Hello everyone, my name is Patrick Enfak. I'm glad to present our work at SaTML. Unfortunately, I couldn't make it to present in person. So the title of the paper is Learning Fair Representation Through Uniformly Distributed Sensitive Attributes. The outline, I will start with the background, give some context and motivation of our work, and so present the methods, then our experiment and the results. And finally, we conclude with the future work. So the increased use of machine learning to make decisions in high-stake scenarios has raised concern about their fairness. In particular, in cases where people's lives can be impacted, such as being granted a loan or not being accepted uh, for a particular school or being released from jail or not. Therefore, it is important to make sure that those decisions are not flawed or, or exhibit some discriminatory patterns. The data we collect to make decisions may contain protected attributes or protected information, such as the race, the gender, the nationality, and so on. And models that we build can rely on those sensitive informations to make decisions. However, protected attributes should not be used as a basis for decision making. And this is enforced either by conventions or law, such as the US Housing Act. So we consider a situation where we have a data set, let's say X, and a sensitive attribute, for example, gender or race, and a target variable. So basically, we are interested in classification problem. So if we build a classifier from X, it is considered fair if its predictions, let's say y hat, is independent from the sensitive attribute, right? This means that regardless whatever the sensitive attribute of people are, the outcome of the model should be the same. And this is what we call statistical parity or demographic parity. So it is shown that simply dropping the sensitive attribute from the feature space does not help because they may exist other features that are correlated with the sensitive attribute. And in some cases, those features are unknown. There's the famous example of using dropping the race from the data set while using the zip code. And people from the same origin tend to live in the same neighborhood. And this happens that the zip code will act as a proxy to the sensitive attribute, and the model will still be using this attribute to make decisions. So we consider our objective is to learn a representation that we call fair representation, such that this representation is independent from the sensitive attribute. We mean that it does not encode any information about this sensitive attribute. It is a more principled way than just dropping the sensitive attribute from into input feature. There's one important constraint here is that the learned representation should maintain the predictive power of the data. So for our target task. And in some cases, it should also produce some reconstruction of the original input. So some related work have addressed this problem using adversary approach, where we basically have a generator part. Here you have autoencoder and a classifier and an adversary. So the goal of the generator part is to defeat the adversary in predicting the sensitive attribute. So the idea is that if this adversary cannot predict the sensitive attribute from latent codes produced by the autoencoder or the encoder and the classifier. Therefore, we can say this latent space does not encode this such information. Similar in this other work where the adversary is called here the critic. However, this adversarial setup is first difficult to converge because it's very unstable, and it is hard to find the right set of hyperparameters that will help the models to learn and converge. And there's another assumption that this adversary will have the guarantee only when the adversary is optimum. It is hard to find this optimum adversary. And sometimes this approach is even counterproductive. So Our goal here is to learn fair representation without relying on adversarial approach, while preserving better or similar fairness accuracy trade-off. So the idea is that we would like to enforce the uniformity of predicting S from Z. We want this conditional to be as close to 0.5 as possible when S is a binary case. So thus, by enforcing this uniformity, we're basically making the prediction of S from Z unreliable. So now I'll present our method. As I said earlier, we do not want to try to defeat an adversary, but we would like to enforce the uniformity of the sensitive attribute prediction from the latent space. So how this works, if we achieve this goal, this means that predicting S given Z is quite almost uniform or exactly uniform. Since we're going to use Z to train a classifier, let's say here it's F, on the upstream task, since Z is independent from S, so we are also sure that on the upstream task, the outcome will be independent from the sensitive attribute. Therefore, we will say that we have achieved demographic parity. So how to enforce this uniformity? The intuition here is that we would like to increase the uncertainty of predicting S from Z. So how? We know that noise is a good way to have uncertainty in the predictions in neural network. So we leverage noisy label space by randomly flipping the sensitive attribute of people or individuals during the training. How we do that? Here we have our architecture. We have a triple loss here. We have an auto cover path, and then we have a network head that predicts the target task. And then we have another network head that we call here our regularizer. So this regularizer is here to enforce the uniformity of this latent space. How we do that? We during epochs, what we do is that instead of training this regularizer heads on the ground truth S, we train it on a noisy version of S. So during the training, what we do is that we compute the cross entropy between the predicted S and a noisy version of X, where some samples, the values were flipped with the probability T. By doing so, we are making sure that this regularization will enforce our latent space to be unreliable when it comes to predicting the sensitive attribute. How? That a question that may occur is that can neural networks fit data with noisy label space? The answer is yes, as shown in this work and other works, that neural networks can fit data with partially noisy or completely noisy labels. So that's what we leverage here to achieve our goal. So as a consequence, if we train a neural network on this noisy label space, what will happen is that the learned model will degenerate, all right? And then it will never generalize well on clean label space. So our regularizer head here enforces the generalization of predicting the sensitive attribute from the learned representation. So basically, if we have a model where we want to predict on a clean label space, it will create the separation between the two classes in this case. But by training on the noisy label space, we notice that in the latent space, everything is entangled. So basically, training on noisy label space enforces the entanglement of the representations when it comes to this sensitive attribute. We also show that if we regularize at multiple levels, we can even improve the performances further. Here, the intuition is that different layers of the neural network can encode different informations. So therefore, if we regularize this level in a hierarchical fashion, we show that this further improves the performances. But regarding our flipping process, we show theoretically that our process actually enforces the network to get the prediction of the sensitive attribute close to the uniform distribution. For that, we show that this optimization problem is an upper bound to the Colbert-Label divergence between the conditional P of S given Z and the uniform distribution. And that you have this theorem in a paper where we basically prove that But just here we consider not a general case, but where we assume that our flipping process follows a Bernoulli and our sensitive attribute also follows a Bernoulli. So the cross entropy between the ground truth and the flipped version is just an upper bound to the carrier diversion. So by minimizing this, we are trying to push this conditional toward the uniform distribution. Regarding the experiment and the result, we experiment on two data sets, the adult data set and the German coded data set. Those are benchmark what we use in machine learning fairness. For the first data set, basically predict if individuals' income is greater than 50,000 US dollar per year, or the German coded data set where we basically classify account holders as good or bad accounts. So we use gender here as a sensitive attribute in both datasets. All components of the model were implemented using linear perception, and then we use a logistic regression model as downstream task, which means we train the classifier from the representation that we learn. So the model that we use, we consider as baseline a logistic regression model trained without any fairness constraints. We also consider autoencoders here just to see the impact of the compression, if this also helps to reduce the influence of sensitive attributes. And then you have other methods such as correlation removal, where it basically tries to find a projection in the way to reduce the correlation between the features. We have adversarial-based approach as I presented. Another approach that uses is adversarial-based, but here it uses Washington distance instead of the cross entropy loss as the adversary loss. So regarding the results, we analyze the learned representation that we have. So what we notice here is that in our architecture, when we train our realizer heads to enforce the real sensitive attributes, we see that if we project our dataset into 2 dimensions and plot them in 2D, we see that there's a separation between these sensitive attributes. So training on the ground truth enforces this separation. But when we train on the noisy label, we see that there's this entanglement in the latent space. Right? And if we compare to other approaches, such as adversarial-based approach, we see that we are basically aiming to the same goal. So here we can see that our method and other are providing the same level of entanglement in the latent space. So regarding the result, what we do is that we compare the accuracy of predicting Y, this is the target task, and the accuracy of predicting the sensitive attribute. So we see that our method here has better or similar performances compared to existing approach. Of course, here the linear regression is has higher performance because there is no sensitive attribute, there is no fairness constraint there. And the prediction of S here, the goal is to make it as inaccurate as possible. This just to check how much information is still encoded in the learned representation. So we see that our method is also providing less performance, smaller performance when it comes to reconstruct S or to predict it using a logistic regression model. Regarding fairness performances, we can see on German dataset that our model provides better fairness. What is interesting here is that we aim at enforcing statistical parity, but this has a positive impact on other metrics such as equal health and equal opportunities. So on both data sets, we were able to achieve similar or better results. So if you compare in terms of trade-off, we can say that our method provides better trade-off than existing approaches. So we also evaluate the hierarchical regularization so that if we have two-layer multi-layer perception, by regularizing only one layer, we achieve this accuracy and this other fairness metric. So we see that if by regularizing further at like multiple level, this can further improve the performances of the model. And then we also check that the adversary in the previous assessments, we use just a logistic regression of adversary that will try to predict or to reconstruct the sensitive attributes. So here, by using a stronger adversary, such as a neural network, we see that our method is still not able to encode much information about the target, the sensitive attribute. So even the stronger adversary cannot accurately reconstruct the sensitive attribute, while we can still preserve slightly better performances from the model. So in aberration study, we study the effect of the flipping probability, where within batches, we randomly flip the sensitive attribute of certain individuals. We can see that the accuracy does not vary much, but we can use it as a hyperparameter that can be tuned. So here we see that 0.5 is the point where we achieve better fairness properties. So depending on the data set, maybe a different probability will be better. So now I will conclude. So in this work, we have presented a straightforward approach to length representation. We use the idea of increasing the uncertainty of predicting the sensitive attribute from the latent space by leveraging noisy label space. Our method provides fast convergence than adversarial approach in the sense that it's more stable, as we just have a minimization problem in the triple loss than a minimax optimization problem. And then we also saw that when we implement hierarchically, it provides much better performances. Overall, we have better fairness accuracy trade-off, and we have tested our method against different adversaries. And then we see that this method is still robust against adversaries that we use to test it. As a limitation, our analytical guarantee of our method does not hold for general for this general conditional, as we assume a Bernoulli distribution. So in the case that it's not a Bernoulli distribution, we cannot conclude that our approach is robust against all features adversary, and this requires further studies in future works. And also, we should be able to assess our work when it comes to multiple sensitive attributes. So here we are just dealing with binary and binary sensitive attribute. In a multiple case, it can be multiple value and it can be multiple sensitive attribute at the same time. So how the flipping process will be done in that case? An idea is that you can just randomly permit or change the sensitive attribute of individual by any of the possible value and do it for all the possible features. So this needs to be more explored. And then our method we should also be able to provide fairness guarantee for people involved in the decision-making process. If our method is used, what level of fairness guarantee they will provide to the users. So I would like to thank you for listening, and I will be glad to hear your questions. Our source code is openly and is available in the paper. So thank you so much and have a great time. Goodbye.